So today I'm going to tell you about a project that we started in 2015. And it involved a large car service provider, I guess you could say, that runs many auto shops in Germany, over 1,000, and has many customers, has a revenue in the billions per year. And what happened with them is, well, I mean, of course, you drive your car into one of those shops, and at the end of each of those lanes, near to one of those hydraulic lift platforms, there would be a little, workplace, a little desk with stuff on it. And that would include a PC, it would include a printer, and various pieces of diagnostic equipment that you could use to look into what was wrong with your car at the time. And in 2015, this company did a strategic shift in their IT strategy, in that there would not and no longer be PCs at every place, but instead every employee would get essentially a fancy tablet, a mobile device. Of course, that caused a lot of issues within the organization, because it meant that these mobile devices could no longer be hooked up to a fixed set of printers and diagnostic devices and so on, because the employees would move around. They would move around from place to place, but sometimes they would also just move to a different site, to a different shop, and they would need to hook up to the devices there. And you might imagine that causes some trouble. So these were Windows-based, and even just printer configuration. If you kind of think that through to the end, it would mean that, every printer would have to be configured on every mobile device, or you would have to configure it as you got to that particular place. So that was just hairy, and with a lot of the diagnostic equipment, it was even more complicated, because you needed to copy, MAC addresses in tiny print from the back of the device into your software and so on. And so what they wanted, though, they wanted sort of the configuration to change as people moved between places. So, and that should, of course, happen automatically, or mostly automatic. And so we ended up writing software for them that did exactly that. Looks like this, so it's not very pretty, but very functional. And what would happen is the software would detect what local network you were in that was specific to each site. And then it would offer you this menu with large buttons that would tell you, the place that you could be at. And you could just punch one of those buttons, and then it would reconfigure your mobile device. So that's pretty nice, but of course it required some work to get it to work well. One of the issues is, of course, that, well, if you configure a printer or any other piece of equipment at a certain place, well, you only want to do that once. You don't want to configure every printer on every mobile device, even if then the software can switch between printers as you move between places. You only want to do that once, and you want that configuration, of course, to be communicated to the other mobile devices once somebody has configured it once. So this is the configuration menu. Also not very pretty, but works. And there, this project was running into a number of constraints before we even got there, because, well, you can imagine in auto shops, at least at the time, networking wasn't very reliable. There was limited bandwidth between sites, and most of that bandwidth was already being used up by software that they already had. And they did not really have the capability of establishing a central server where you could keep configuration information. Even if you did have a server, its value would be limited, because, see the points 1 and 2 there, because of the unreliability of the network. And so we ended up thinking about this in terms of peer-to-peer synchronization. So the idea was just that the mobile devices, they would talk to each other and exchange configuration information as it got generated. And we wanted to keep things simple, so eventually we boiled it down to just doing pairwise synchronization between two mobile devices. So the idea was this, right? Is anybody made a configuration change on any device, immediately that device would broadcast a little packet on the local network, notifying all the other devices, hey, I've got something that you might be interested in. And any other mobile device that was interested in that change would then hook up with the first one, and they would do something that I'll tell you about to synchronize and to exchange all the data that was missing on each device. Also, when somebody was moving between sites, so would drive onto the parking lot of a site, the mobile device would log into the Wi-Fi there, and would also send a broadcast and say, hi, hey, I am new here. Does anybody have configuration information? Would anybody like to pair and synchronize with me? And then kind of the same thing would happen as in the first scenario that I told you about. So maybe hard to believe, but, doing functional programming, we live kind of in a special bubble. And at the time, we didn't know event sourcing was a thing. We didn't even know the terminology around it existed. So we thought about this problem in terms of facts. And we'll see that it's very much like event sourcing, but there's some subtle differences. None of them are particularly important. But we figured, a fact is not, that site has this printer. That place has this printer, but a fact is, Mr. Miller said, on this date, on the 10th of October at 1400, that indeed this place, had this printer. And of course, that continues to be a fact because in all future, right, Mr. Miller will have done that at that certain time. Of course, it might happen that a later fact, as far as the configuration is concerned, kind of supersedes or obsoletes an earlier fact. But that doesn't really detract from the fact that, the set of all the facts is something that just grows. You just add facts. And I think you can immediately see the analogy with event sourcing. And so as we synchronize facts, right, it's really much simpler than having a full-on distributed database. I'm sure you know all about this. The only thing that you need to do is you need to make sure that, you figure out what facts are missing on one device that the other device has and vice versa. And then you essentially just want to communicate those facts and not all the other facts, right? Because as time, as time goes by, you accrete more and more and more and more fact, and you don't want to exchange all of them, especially if the network is unreliable and network capacity is limited. So we really, and whenever you do this kind of synchronization, I'm sure many of you know this, but I'll just go over it briefly. Basically, the mother of all synchronization algorithms is something called a Merkle tree, which I wish I'd learned about when I was still studying computer science at the university. Very useful data structure. And the way it works is this, right? You have at the bottom, you have your data. In our case, it's the set of facts. And what you do is you compute a hash for each block of data, for each fact. And you use the bits in that hash to create a path in that tree. So you use those hashes to arrange a tree on top of your data. And then what you do is on the internal nodes of that tree, you store composite hashes. So if you have a node that has 3 data blocks underneath it, you will take those 3 hashes, combine them into one hash, and you will combine them more and more as you go up. And this is the basis for a pretty simple synchronization algorithm, because as 2 mobile devices meet, you just compare the top hashes. Those represent the totality of all the blocks of all the facts in the system. And if they're the same, then the 2 devices are already synchronized. And you can just put that hash in that broadcast I told you about earlier, and then no further interaction would be required. If they don't agree, you just move one level down in the tree, and now you have 2 hashes to compare. Maybe one of them is the same, and then you can ignore the entire subtree underneath. And maybe the other one is different, in which case you will move further down and further down until you reach the block level and you have a list of blocks that you actually need to convey to the other side. So that's the idea of sort of Merkle tree-based synchronization algorithms. Since at each step you're kind of sending information to the other side and they kind of exchange information, I like to think of it as kind of like the exchange of Japanese business cards, right? Where there's this little ritual that people use to really, in one move, exchange 2 business cards between 2 partners. So, to implement this, we used, I guess by now, pretty standard technology. Back then, it was still pretty unusual, at least in Germany. So this was implemented in F#, of course, because we do functional programming. UI was done with the regular tool stack in .NET, and we use SQLite to do data storage. Those held up pretty well, except maybe for the WPF part, but that would be a different story. So, this sort of approach to implementation already gave us a lot of immediate benefits. The most immediate benefit was that we got an audit log, especially in the early stages of the software. Sometimes things went wrong, and of course, then everybody tries to blame the software vendor. But then we had a record that said, "Oh no! Well, did you ask Mr. Miller if indeed on Saturday at 14:00 he changed the configuration to that other printer, and maybe that's where it went wrong." And sure enough, that's where it went wrong, and it wasn't the software. Also, people see the software as kind of cool because it seems like magic to them that the mobile devices would automatically update without them having to do anything. Internally, a lot of people talk about this as a virus, right? And in joking, but they think it's really cool. And in some funny ways, it's used as a strange social network because people notice when the CIO, for example, drives onto the parking lot because he brings with him a mobile device that has the configuration data from sites that they haven't heard of yet. And so when they see their list suddenly showing sites that they've never heard of before, they know the CIO has arrived and they use it. And that's sometimes the subject of sort of break banter, which I found kind of interesting. But we'll get back to the hard facts. I'm just going to briefly tell you that it's really easy to implement this kind of synchronization algorithm in a functional language such as F#. You just do that, of course, using a function. So we represent a Merkle tree that could also be a Merkle subtree as a combination of what's called a signature prefix. So the signature is the path along from the root to the node in the tree, and the signature prefix is just the prefix of that path that leads to a particular subtree. And then at an internal node in the tree, we keep a list of hashes and the full signature of all the blocks underneath that we might want to exchange. And well, each signature, as you can see, is just a list of numbers. For exchanging information, we just use what's called a fingerprint, which is a signature prefix. So it's the location of a subtree and the hash at that location. And the two parties to a synchronization just exchange one of these messages. One of them is, I have fingerprints. So I want to tell you about a bunch of fingerprints that I have that you might not have yet. And at the bottom, once we've reached the bottom, we'll just tell you about the hashes of all the blocks that we've now found out that you don't have yet. And we can then cast that into a function called a synchronization round, which does one level in the tree. You just give it all the hashes in the system. You give it a set of Merkle subtrees where the algorithm has not determined yet that they are, where the algorithm thinks that there might be parts that are different between the two. And then there's a message that you got from the last round, and then it emits either a message to give to the other side on the next round and a new Merkle tree set or a list of hashes of blocks that need to be communicated. If F# is not your thing, don't worry about it. We'll get off the F# code in just a moment. And we're not going to look in detail in this piece of code, which is the full actual production synchronization algorithm. Actually works pretty well. And you can see it's not that many lines of F#, and it actually follows the strategy that I told you fairly directly. Still, should tell you about this also. This is actually stuff that I wrote at the time, and I didn't have much time to communicate with the other team members because I was traveling. I think I was in Canada at the time, on some conference. And so I really was required to write it in a very generic way. So what I asked them to do was provide an object of this type, synchronization context for blocks of type A. So it's even generic over the concrete block representation. And you just give it a couple of functions. So I forget what the protocol mode is, but you give it a hash function for your blocks. You give it a pickler for serialization. You give it a function that extracts all the hashes from the database or whatever it is. You give it another function that retrieves the actual data blocks for the hashes, and you have one that stores blocks once you've received new blocks through synchronization. And you provide that, and then I give you the code that does the full synchronization. And that worked exceedingly well as an interface. Now, one issue, though, is that still the algorithm for this is pretty gnarly and complicated. It does pretty complicated bit fiddling. And so there's a lot of potential for bugs. Also, we knew that if we were not going to get this algorithm right, then there would be major problems because the configuration would not be right. The shop could not work. That means lost revenue, and tens of thousands of euros pile up within hours very quickly. And we really wanted to avoid that, so we knew we had to get it right. It's not directly related to event sourcing, but this being an experience report maybe helps you anyway. So what we did is we implemented a local synchronization algorithm that doesn't go over the network. So it's just the core of the algorithm. So in go, two lists of blocks, BS1 and BS2, blocks 1 and blocks 2. And it returns two sets of blocks that are just exactly the blocks that need to be communicated to the other side as a result of synchronization. And what you do is on each round, you do a loop. Each iteration of the loop, you do one synchronization round on each side. And you either retrieve the blocks, or if you're done, or you just loop on to the next round. So, and you start with a top Merkle tree. Don't worry about this piece of code, doing fine on time also, but really this It's just to show you it doesn't take a whole lot of code to then implement functionality on top of the basic algorithm. And now this you can use as the basis for testing. And in case you aren't familiar with it, unit testing is really terrible for this kind of problem because there's just many, there's many combinations of bits that the algorithm treats differently. And so you're sure to miss some edge cases if you just do example-based unit tests. And so we use property-based testing, where you say, well, I don't want I don't want things to work out all right for a particular set of blocks, but I'm just saying for all blocks. So if you read it from top to bottom, it says, prop for all, and then it says for all arbitrary sets of blocks of bytes, and another set of blocks of bytes, and we're going to call those BS1 and BS2. The following property should hold. And the property is, well, we're just going to take those two sets of blocks. We're going to combine them using set.union. That gives us all the facts that are in the system. And then we will run the synchronization algorithm that will give us two sets of blocks, BS1 prime and BS2 prime. And then two conditions or two sets of conditions should hold, namely that the blocks that we're getting should not intersect with the blocks that we already have. We don't want to get blocks that we already have. And so we just use set intersect to compute the set intersection. And though that intersection should be empty, that would mean the algorithm is efficient. And the property at the bottom says, well, if we combine via set.union the blocks that we have with the blocks that we're getting, then we should have all the blocks. So the algorithm should also be correct. And so this is, this is essentially the only relevant test for the core algorithm in the system. And it found literally all the bugs, or I'd like to think all the bugs in the system, because since deployment 6 years ago, we found exactly 0 bugs, and it's worked extremely reliably in practice. Anyway, so much for synchronization. But, well, if you know your event sourcing, you know that there's a couple of other issues that you need to deal with. One is that there's at least a theoretical potential for conflicts, right? It might be because we now have, a system where there's many mobile devices, and in principle, somebody could enter configuration information on one mobile device, and somebody concurrently does that on another device, where concurrently just means that they haven't synchronized yet, right? It doesn't mean that it really has to be at the same time, because things are really loosely coupled here, and then you might get a conflict, right? And in this, we thought this would be really rare in the beginning, because we figured when you configure a device, you're standing right in front of it. You're standing at that place, and you would notice if there's somebody around you standing at the same place also doing configuration. But for reasons that we could never figure out, it would happen quite frequently that there were conflicts, and then a screen would pop up looking roughly like this one, where it said, here, Mr. Müller and did this, Mrs. Mayer did this, which one is right? And we didn't think about, because we thought it was rare, we didn't really invest a lot of care into implementing this. Particularly, we didn't think about the fact that, of course, as the efficiency of the synchronization algorithm would mean that typically all the mobile devices at one site would show this concurrently, right? At the same time, the screen would pop up, all the employees would go, what is this? It would be good if just one of them pressed that button if they communicated, but they usually don't have the time. So in panic, they would push some button, and that would not always resolve the conflict. And so, we were quite happy with sort of the internal representation in the code here that you can see. So the code kind of represents a value that it gets from synchronization by this optional val type, which says, well, it might be some fact about a particular piece of equipment. It might be absent. It might be good. It might be good value, or there might be a conflict. And in case of conflict, it gives you all the information that you need to resolve it. So all the different versions that there are of this particular fact, and which user entered that fact on which machine and what time. But the problem was really the UI. It wasn't the internal representation. And at that point we realized, oh, we're really doing distributed systems here. We didn't really think about it in those terms before. And of course, then you get all the problems that you tend to have with distributed systems, among them inconsistency. So, so I have this problem, and it's not just, everybody gets confused, but even if people push the right button, Mr. Müller, Mrs. Mayer, Mr. Jones, and Ms. Smith, they all push a button. What the system would do is it would create what's called a merge record. And here you can see that the system tracks causal dependencies between facts. So it says, for example, in the distant future, you might have configured some old Epson printer. And then somebody says, well, really, now we have this Acme localized 5020. And somebody else says we now have the Acme 5021. And these errors would be tracked in the system in that they supersede this Epson FX80 old printer. And once somebody pushed that big red button in the conflict screen, what's called a merge event would be created, or a merge fact would be created that would be recorded as reconciling the previous divergent facts that were in the system. And so the user experience was terrible with this. And so we figured, well, really, we could automate this, right? We could, instead of having the user push a button, we could just push the button for them. And then it would look like this, right? There would be an automatic merge event created. And we didn't think this through, right? And, this was after the first release, so we were a little stressed out. So that would be my excuse. But, now it was like a lot of monkeys were pressing buttons, creating merge events. And these, again, had to be merged in order to create like one single truth to bring together all of those divergent arrows. And so fortunately, when that happened, we kind of noticed after 10 minutes that the database just kept growing. And then, then we were able to fix that problem. So eventually what we did is we said, well, we're going to just pick any of the current leads deterministically. Often they agree. And even when they don't, you just pick any of them. Even if you pick the wrong one, the wrong configuration, people will notice pretty quickly. And then hopefully one person will go and fix it. Or sort of asymptotically, people will notice that people can keep fixing and unfixing it, and then they'll communicate enough to then fix the configuration problem. And only when there's a manual change, we would then create a merge record, as I explained before. So that's how conflict resolution now works in the system. It's completely in the background. And we worried about it a lot at the time. Oh, these conflicts, we've got to have a good strategy for resolving them. But then, we kept removing more and more code, the automatic merge resolution, the manual merge resolution, we just removed all that code, and users magically were much happier. So all of our computer science nerd thinking was we probably shouldn't have done that. Anyway, but this sort of fancy representation of causal dependencies and of the history of the changes in the system then brought new ideas in. So one of the things that we noticed happened was that the users would say, well, Mr. Mayor yesterday screwed up the configuration at our site, and we wish we could go back to the configuration of the previous day. And of course, doing something like event sourcing, you can go back in time. We just never thought about providing that information, that kind of capability to the user. But then the users told us that would be really useful. So we put a screen like this in, which gave you a time machine where you could look at all the previous configuration of the system. It would even summarize who was the last person to make a change. And you could then just pick the right one and go back to that configuration. And that proved to be supremely useful in managing the system and getting site configurations to a stable state. Now, I promised I'd talk about projections. And indeed, the system originally had we didn't know it was called projection. We just called it a locality map at the time. And the idea was that we thought we need a fast lookup if somebody goes into a particular Wi-Fi net to look up, well, what site is that Wi-Fi subnet associated with? And so we had like one little table in the database, the locality map that would map the subnet to the site. And then from then on, we would read all the site information. And we could never figure out why, but then we got bug reports that the locality map was inconsistent and it wasn't finding the site associated with the subnet. And we couldn't figure out why. I looked for the bug for a while. I couldn't figure out why the locality map was getting inconsistent. So I figured I might just try taking it out, right? And just iterating over all the available subnets in the database looking for the subnet and seeing how fast it was. And it turned out it was plenty fast. We never should have put in the locality map, the projection in the first place. And so I just put in a change that ripped out that piece of code. So you're seeing a pattern now, right? Is that we kind of overthought and over-engineered the original system. And then as we took things out, the user experience improved. So in particular, that was the case here. Maybe it's worth talking a little bit about the database schema that enabled this. Again, remember that we weren't thinking about this in terms of events, but in terms of facts. So it's very simple, very primitive. There's just two tables. One of them is called hashes, and it tracks all the hashes of all the facts in the system. And you see that there is a field there called obsoleted hash, which says that, well, this fact made another fact obsolete. So, that new printer made that old printer, the fact that Ms. Mayer just announced that there's a new printer made the old fact that Mr. Müller announced the old printer many years ago makes it obsolete. So we'll track that. And then you see that this table is indexed by the obsoleted hash. And then there's just a simple table key value, which just tracks key value pairs of properties and values. There's also a GUID field to make links between entities in the system, but that's kind of coincidental. Of course, there's the hash, and there's some metadata about that fact to track, who did this and when did they do it. But again, that's not essential to this model. And again, we would also index this by GUID and property. And these two tables enabled us to just create a simple view. Remember, this is SQLite, and very simple. What it would do is it would eliminate from the key table, the key value table, just those facts that were obsoleted. So we were then looking at a very simple table that just had current facts that were still current, and everything else came from that. And that, as you can see, it's very simple. It also allows you to very easily extract, for example, all the facts associated with a particular site or with a particular place. And this meant that you could do a lot of sort of lookup operations without having any sort of projection in the table. Arguably I lied, though. There is a projection in the system, but it's just residing in memory. It's not in a database. It's not persisted. And that's I'm just putting the beginning of the type definition here, where we're just representing a locality, which is a site or a shop. And you can see here that it has a name. There might be a little server standing at that particular site. It has a subnet, and then there's places associated with it. So this is a good old data model, right? And you can see here that kind of structuring the database around facts kind of forced us to really make a very strong separation between the data model and the database model. And you being from the event sourcing community, that's one of the key benefits of using event sourcing. But it also meant we had no database model at all, no database projection or anything else that we would have to synchronize with. The data model and the software itself. And actually, if you try to put this into a relational database, then it would be a pretty elaborate and complicated model. And then there's just an explicit function called read locality, which, again, this is the actual current production code that just reads it. It's just an old-fashioned read onto the database and would reconstruct that locality object from the facts in the database, and then that would be really nice to operate on. You can see here, if you're interested, you can see that DB curly brace, which means all of this runs in a free monad in F#, and the free monad allows us to do dependency injection. In particular, what we can do is we can swap out the actual SQLite database for an in-memory RAM database. And that can be used as the basis for the time machine, because for the time machine, what we do is we just extract all the facts that are relevant for a particular point in time, create a virtual database for that, and then run all the usual functions to recreate the state from there. What you can also do if you have this kind of in-memory projection, I don't know if it qualifies as a projection, is you can have several projection objects in memory at the same time, and you can compare them. So in particular, here's a function that takes some old locality and a new locality, and it would extract two things. It would extract a representation of all the changes between those two localities that you could, for example, display in the UI, and it would also get you a list of database operations, or a database operation that would convert the old locality into the new locality. So in order to implement the time machine, all that we had to do was we had to reconstruct the locality object that was associated with the point in time in the past, run this function here, apply all the database operations, and we would be back in the old state. And all of this kind of came together, the representation of facts with the dependencies that we tracked, the in-memory projection, if you will, the locality data type, the time machine, all of these things then came together very nicely. And so we were quite pleased with the end result. So I'm I'm actually done with my experience report. I'm not sure there are sort of general conclusions to be drawn from this. It was one project that we did. It was really at the beginning of a long sequence of projects that we did using event sourcing, once we figured out the terminology. But, we've tried to push some of the benefits into other projects as well. And these are some of those benefits. So first of all, when you do something like synchronization, it's a good idea to separate the event model from synchronization. You might have noticed the synchronization algorithm doesn't even know it's dealing with events or facts. It just thinks about data blocks. And that's something that's possible. And because it creates decoupling, it's also something that's desirable. Mostly we've avoided creating projections, at least, persistent projections in a database, through the use of these explicit dependencies that would immediately filter out sort of obsolete facts that were still in the database, and a very modest amount of indexing. I'd like to think it's clever, but it's actually not very clever. It's just there's only a handful of fields that you might index, and so you could probably just index all of them without too much overhead. Even if you have a persistent projection, it makes sense to create an explicit in-memory data model that's really a proper data model, and that's independent of the structure imposed by, for example, a relational database. And this gives you a lot of freedom then in your software to actually handle it, to do things like the stuff that we did with the time machine, which is much harder to do if your projection just lives in the database, as you might imagine. I realize really that I think with event sourcing, I see a lot of people talk about the fact that you can go back in time, but often that functionality is never offered to the user. And I would like to encourage you to think about providing time machine-like functionality to the user. Here's how the user can go back in time, not just for administrative type tasks. This is all basically following, the general thing that we should always be doing in software architecture, which is to decouple all the things. And you might have noticed we decoupled the synchronization algorithm from the facts representation. We decoupled, the database representation from everything that was in the core software at all. It was very generic, very primitive model. And then we have a proper database data model in the software that can work completely without a database behind it, right? Once you have that locality.t object, then you don't need to worry about the fact that there's a database that you need to talk to. And of course, it allows you to then manipulate the database in all kinds of ways. Also, the abstractions that we have in functional programming, of course, help. Now, I think in the abstract, I said something that really, of course, we did this without CQRS because we didn't even know those 4 letters existed at the time. But, reading about it afterwards, I always thought that, the CQRS, the terminology has never been really helpful for us in structuring applications. The read model and the write model, it makes no sense to me actually to sort of divide things along those lines. And I don't think it's a very good guiding principle when you actually design your application. I think the way you should think about this is, well, your event store, your events are sort of your primary storage, right, for what happened in your application. They're the single source of truth of what goes on. And, your application sometimes wants to ask questions, wants answers to particular questions. And you should think about those questions, right, that you want answered. And you should think about what is the most efficient way to get them answered. So in our particular case, the question was really simple. So one pretty simple question that we asked was, well, what is the configuration of that locality? And it turned out to answer that question, you don't need a read model, right? It isn't necessary. I think if we would have thought about this originally in terms of CQRS, we would have created an explicit read model that was essentially pointless and that would have blocked our way to then implementing things like the time machine functionality that I told you about. So really, you should think about, you have your event store, you should think about the questions that you want answered, and you should think about you should think about the means that help you answer them efficiently. Those means might be a database, right? Store them in a database, that's fine, but it might also be something that you can answer directly using the events at hand or some other means. And I think that is, or for us at least, it's been more helpful structuring applications then, and I don't think we ever talk about sort of, oh, but where's the command query responsibility separation? It's just not something that we think about or that we talk about in our day-to-day work. Okay. I think that's all I have to say. I hope it was a little bit interesting for you, and I'm happy to answer questions. I think we have some Q&A area set up that we can move to.